reaction in both laboratory and pilot scales. Dr. Odeodaya had his BEng in chemical engineering from the University of Maiduguri. His MEng and PhD in chemical engineering were then obtained from the Nnamdi Azikiwe University, Awka. In addition, Jerome has a Doctor of Engineering degree in Waste and Resource Management Engineering from the University of Rostock, Germany. The doctoral degrees were respectively sponsored by the PTDF and the German Academic Exchange Service. Dr. Odeodaya also has a certificate in data science from the WBS Coding School, Berlin, and he is an MS student of nuclear applications at the University of Applied Sciences, Aachen, Germany. As a lecturer, Dr. Odeodaya previously taught at the Department of Chemical Engineering, Modibo Adama University, formerly Federal University of Technology, Yola, before moving to the University of Port Harcourt. His research interests include waste valorization, nuclear waste management, corrosion studies, microbial community analysis, techno-economic analysis, and life cycle assessment. Ladies and gentlemen, I present to you our guest lecturer for today, Engineer Dr. Odeodaya. Please, you have the floor.
Thank you very much, sir.
You're welcome.
Please confirm that you can see my slides, sir.
You can see it.
Okay. Just a second, please. All right. I want to thank the members of the organizing committee of this seminar for the opportunity to share my experience on this platform with you. And indeed, that is what I'll be doing this morning, sharing my experience on the subject matter as it relates to my successes and, of course, my failures when it comes to Ensiling for microbial chain elongation. By the way, good morning, everyone, and I am really glad for this opportunity. In the course of sharing this experience, we'll be taking a look at these outlines, beginning with Ensiling as a pre-treatment process, and then we take a look at the Ensiling process itself and what it will eventually be used for, that is chain elongation, the product of chain elongation, the factors influencing that process, and the economic viability, if any, of the chain elongation process. I would like to begin by saying that Ensiling can be seen as both a pre-treatment process and a preservation process. Now, we all know that one of the greatest challenges to the valorization of biomass is lignin degradation. Now, this explains why different pretreatment processes like the chemical pretreatment and the hydrothermal pretreatment have been used to pre-treat biomass in preparation to their valorization. Each of these pretreatment processes tend to achieve the same aim, that is lignin degradation, such that the cellulose and the hemicellulose can be made available for hydrolysis, enzymatic hydrolysis, and subsequent fermentation to an appropriate biofuel. Now, but we know that these pretreatment processes usually produce inhibitors that could affect downstream processing. In addition, we could have a situation where there will be loss of sugar because after chemical pretreatment, for example, the biomass is usually washed, as that washing could lead to a loss of sugar, which are needed for the fermentation process. And of course, that washing also increases water consumption. And in the case of hydrothermal pretreatment, it could require high temperature and pressure. But ensiling seems to be different. During ensiling, we have a situation where you have a biomass, for example, like this grass we see here, which inherently contains water-soluble carbohydrates. So this water-soluble carbohydrate in the biomass will be acted upon by inherent bacteria, or in some cases, lactic acid bacteria can be applied. And where this lactic acid bacteria will now convert the water-soluble carbohydrates into fermentation products like lactic acid, acetic acid, ethanol, and butyric acid. These acids, especially lactic acid, reduces the pH of the system, sometimes and in most cases up to less than 4. This low pH ensures that there is little or no unwanted microbial activity. So the system is kept that low, and since there is no microbial activity, the system is now, the biomass is now preserved until a particular time that it is needed. Now, it is important to state that the primary substrate for ensiling is water-soluble carbohydrates. That explains why substrates like fish waste, for example, are usually difficult to ensile because fish waste does not contain water-soluble carbohydrates. So in order to, if a substance or if a biomass does not contain water-soluble carbohydrate, one way of still ensiling is to add the water-soluble carbohydrate to the system like molasses. So ensiling efficiency increases with water-soluble carbohydrate content. So the higher the water-soluble carbohydrate content of a biomass, the greater the efficiency of the ensiling process. Now, it is instructive that the goal in ensiling most times is to produce silages that is without butyric acid. This is because butyric acid, the formation of butyric acid is an unwanted fermentation process in silages. For example, in animal feed, butyric acid reduces palatability. It reduces the nutritive value of the silage, and it can also lead to reduction in milk production of the animals. And of course, in biogas production, butyric acid leads to higher loss in volatile acids. Maybe I should explain this a little. Now, we all know that during biogas production, the volume of biogas produced is usually measured in volume per mass of volatile solids added. Now, so the question more sometimes is, what is the mass of substrate that will add that will give us a given amount, a given mass of volatile solids? The mass of volatile solids sometimes that we use is usually determined from the organic loading rates, the volume of reactor, and the days of operation. And so to get the biomass required to give us a given mass of volatile solids, we usually divide that mass of volatile solids by the total solids and the volatile solids. So in butyric acid fermentation, if there's a higher loss in VS, it means that we'll need more substrate to give us a given mass of gram volatile solids that is required. Now, apart from preservation, these acids also help in pretreatment in such a way that they delignify the lignin component of the biomass. Take a look at this that we've done sometimes, this is from the effect of ensiling on the structural carbohydrate of cassava peels. Now, these are the physicochemical parameters of cassava peels before ensiling. And these are the ones, the physicochemical parameters of cassava peels after ensiling. And we can see that the ensiling process significantly reduced cellulose and hemicellulose. And this is because the cellulose and this is because of the hydrolytic effect of the acids that were produced during ensiling. And as you can see, the ensiling process also significantly reduced the pH. At the start of the experiment, the pH was about 5.8, but after about 300 days of ensiling, the pH was now less than 4, with a significant quantity of lactic acid, acetic acid that were produced in the process. Of course, ensiling usually in all cases leads to a loss of volatile fatty acid. The formation of all these fermentation products always lead to a loss of volatile acids. However, if butyric acid is formed, the loss in volatile fatty acid, the loss in volatile solids is usually higher. And of course, ensiling also reduced cyanide. In another study that were done from some other authors, we see a situation where they showed this SEM micrograph. There, it gives a detailed information on the surface characteristics and the physical structure of the biomass. This is what we see here. Now, as we can see, the surface morphology of the silages is shown at two different magnifications. This one is at 500 times the magnification. This one is at 1,000. Now, the untreated substrate, which is the one you see here, the untreated substrate had noticeably solid and rigid orientation, which was attributed to the lignin substance that covered the surface of the biomass. But we look at other silages that were pretreated at different conditions, which it showed that is a pronounced physical alterations and porous surfaces. Now, the morphological changes was a consequence of low pH, or if you like, what we call acidolysis, or if you like, enzymatic degradation of the lignin. So the point is that ensiling, apart from being a good preservation process, is also a good method of pretreatment of biomass, as we see here. Now, we have successfully used ensiling to pretreat water hyacinth, which we coincide with maize straw, and we have also used it to pretreat cassava waste. So, just like every other pretreatment process, ensiling has its own drawbacks as well. The first one is that it takes time. Before ensiling will have a pretreatment effect on a substrate, it has to be for a minimum of 120 days at least. I have not seen a situation where ensiling had a pretreatment effect on silages less than 120 days. So that is one thing. It is time consuming. Of course, it is because the acids responsible for this pretreatment are all weak acids. So it certainly takes time. Another thing is that there is always a loss in quality during feed out. Feed out is that time where we take out the silage from the silo to feed into the reactor for a given purpose, maybe for anaerobic digestion or for fermentation. The best, maybe to explain it better, I have to show you these pictures. Now, the picture you see here was sugar beet leaves that has been recently graded in preparation for ensiling. Now, the next picture is the sugar beet leaves with after ensiling for 370 days. As you can see, the color has changed from green to greenish yellow. And indeed, this is a typical coloration of a substrate that has been properly ensiled. Now, the third picture is that same silage that has been exiled for 370 days. The difference between picture 2 and picture 3 is that picture 3 was taken about 5 minutes after exposure to air. Indeed, silages tend to lose their quality when they are exposed to air. The extent of the loss in quality is a function of the duration of exposure. The longer we expose it, the more they tend to lose their quality. So the question now is, if this is so, because silages will always be exposed when you want during feeders. So how do we prevent this deterioration? Now, what we did was now to look at ensiling these sugar beet leaves in tall vertical columns, as you see here. These vertical columns were about 3.7 meters high. We ensiled it in such a way that at some given point in time, we're able to take out silages from 5 different points, 1, 2, 3, 4, 5, to test for their quality with time. Now, after about 300 days, we found out that the quality of the silage at any given point, we are not significantly different, except the one here that we obtained from the top. The ones here at the top were significantly different in terms of the total solids and the volatiles of it, maybe probably due to the effect of gravity. However, what this simply means that when we want to feed this silage into the reactor now, since the TS and VS at this top here were significantly different, what we did was to vary the organic loading rate when we got to this point. However, we found out that it was not only the TS and the VS that were significantly different, even the concentration of acid, the fermentation product at this point were also significantly different. So in order to arrest that, what we did in the second experiment we had was to compact this headspace that we had here, was to fill it with inert materials such that the substrate became more compacted. Under that circumstance, there was no longer any significant difference in terms of the fermentation product and the TS and VS at any point in this, in the columns. It is important to state that silages are often used to provide continuous and consistent supply of substrate whenever required. It is especially used for substrates that are available seasonally. In our case, when we first had it, we used sugar beet leaves. Now, sugar beet leaves are only available around October, November, when the sugar beets are usually harvested. After that time, we no longer have it until next winter. So in order to make it always available, ensiling is a good method of preservation of that substrate and its treatment. We also find out that the highest possible proportion of the original nutritive value of the substrate is always retained, irrespective of how long, provided it is properly ensiled. Provided it's properly ensiled, we can have the highest possible proportion of the original nutritive value retained. We had this sometimes published sometime in Biofoil. So now, after ensiling, which we use as a pretreatment process, the next question is, okay, what do we use it for? Now, microbial chain elongation. Now, microbial chain elongation involves the open culture of complex waste into valuable chemicals. Open culture because most of the inoculum that are used are not engineered. We just get them from open sources. Now, it is an anaerobic bioprocess, specifically for medium chain carboxylate production through a process that we call reverse beta oxidation. Now, during chain elongation, short chain carboxylate like acetic acid and alcohols are converted into medium chain carboxylates via fermentation. Now, ethanol or lactic acid are often used as the electron donors. So we can either use ethanol or lactate, but the process is usually simple. What happens during chain elongations is that two carbon atoms are usually added to a short chain carboxylic acid serially. So for like in this case, we have acetate, which takes two carbon atoms from ethanol to form butyric acid. The butyric acid takes two carbon atoms again from ethanol to form caproic acid, and the reaction continues in that order. Now, in this case, since we are beginning with acetic acid, then what we'll have are even numbered carboxylates. Even numbered medium chain carboxylate is what we'll have. However, when we use propionic acid, then in that case, we'll have odd numbered carboxylate. As acetic acid has two carbon atoms, propionic acid has three. Now, just as I mentioned, we can use ethanol or lactic acid as the electron donors. But it is important to state that thermodynamically speaking, it is more feasible for microbial chain elongation to be obtained when ethanol is used rather than lactic acid, as seen from the lower values of the Gibbs free energy reaction. Now, as I mentioned, this microbial chain elongation is used for the production of medium chain carboxylate. So what are they? They are basically carboxylate with 6 to 12 carbon atoms. Now, the most common ones are the caproic acid or caprate, which has 6 carbon atoms, and the caprylate or caprylic acid, which has 8 carbon atoms. Now, compared with other biorefinery products like ethanol and biogas, MCCs, the medium chain carboxylate, have a higher energy density, higher product value, and broader applications. As you can see in this table here, the current prices of some of these products are here listed. See that the cost of caproic acid compared to ethanol and these other short chain fatty acids are the cost of caproic acid is by far higher. Now, as I mentioned, that medium chain carboxylic acids are extensively used in the food and pharmaceutical industries. In the food industries, caproic acid is used as spices and as preservatives. In the pharmaceutical industries, caproic acid is used as a vital precursor for specialized medications and therapeutic formulations. In fact, some of these medium chain carboxylates are also used as precursor for the production of sustainable aviation fuel. And so there are different factors influencing MCC production. One of the very important factors is what is called the nature of inoculum. I will demonstrate it using these two data. Now, figure A here is figure A shows the product obtained when we use a digestate from a biogas reactor as inoculum. For figure B, we use a fermentation broth from a reactor that was already producing caproate as inoculum. The aim was to produce medium chain carboxylate, which we represent here as C6 and C8. Now, our observation was that when we use digestate from a biogas reactor, we did not notice any meaningful production of C6, represented here in red, at all until maybe close to the 40th day. In fact, it was only on day 50 that we got about 0.5 gram per liter of capric acid. Now, it was after this time that the concentration started rising again. Now, it is important to state that since we are using a digestate from a biogas reactor, the digestate was populated with methanogens. Now, the formation of methane or the production of methane is a competing pathway to the chain elongation process. So if we use an inoculum that is populated with methanogens, then it is very unlikely that we'll get a significant amount of medium chain carboxylate. So what we normally do is to autoclave the inoculum. Now, methanogens are non-spore forming. So when we autoclave it, the autoclaving tends to inactivate the methanogens. Unfortunately, some of the microorganisms that are responsible for the formation of medium chain fatty acids are also non-spore forming. So in the course of autoclaving to deactivate the methanogens, some of the organisms responsible for medium chain carboxylates are also inactivated, at least for a long time, because it was until after from day 50 that we started to notice the significant production of medium chain carboxylate. But throughout the 71 days of operation, there was no production of C8, caprylic acid. We didn't have that at all. Contrast that to the second graph, where we had a situation where we used inoculum from a reactor that was already producing caprate. Right from the beginning, we had the production of capric acid, and even C8 was also formed as well. Now, if you notice, after this 17, there was a radical drop in the production of C6. Now, this was because usually during fermentation like this, trace elements are usually added. Now, we had a cocktail of trace elements which we usually add into the reactor. Now, trace elements are essential micronutrients in microbial chain elongation. They act as vital cofactors for the specific enzymes required to convert short-chain fatty acids into valuable medium-chain fatty acids. Now, what I cannot remember now is why we did not add it. The point is that we did not add it on this day, whether it was because we forgot or that we were expecting a replacement. One of these two things happened. It's like what we ordered came late. I think at the beginning of the experiment, we knew that much of it was not remaining. So we placed an order. However, it took time for it to come. So within these days, it was not added. That was why we had this sharp drop in the concentration of medium chain, especially capric acid here. So when we added it again, the concentrator started rising again until we ran out of feedstock. Now, we carried out a microbial community analysis. We just wanted to know what type of bacteria were here, what type of microbial community were here. And we did this, plotted it on an NMDS plot. Now, the non-metric multi-dimensional scaling plot, as you see here, is a distance-based technique. You see that the distance between this community and this community is an indication that they were significantly different from each other. Now, however, it is important to state that at the phylum level, the microbial community in both A and B were the same. They belong to the phylum Firmicutes. But at the genus level, that was where we now had the significance difference. While this B was populated with caproseprodicins and the Clostridia, the population of these important medium chain carboxylate producing microorganisms were at very low amounts when we use a digester from a biogas reactor as the inoculum. Even from the kinetics that we use using an appropriate equation, we find out that medium chain carboxylate here was not produced until from the 10th day. That was now when we started noticing something very small. But here, we see that there was basically no lag phase. It just started producing almost immediately. So maybe the lag phase here maybe due to the autoclaving, or maybe because they were in very minute quantity and needed to acclimatize more to the environment. That was why we had it starting very late at this point. But however, as I mentioned earlier, C8 was not even produced at all. And in another experiment again that we did, we used 3 different inocula. We used leachate from a dump site, we used ruminal fluid, and we also used digestate from a biogas reactor, just to confirm. The aim again was to produce medium chain carboxylates, which is C6, C7, and C8. Now, as we can see here, where we had the highest concentration of medium chain carboxylate was when we use leachate from a dump site, and then this leachate from a dump site as inoculum performed better than the ruminal fluid. Of course, the biogas digested from the biogas reactor, there was no C7 or C8 at all, just small amount of C6 that we had from here. So this goes to show that the nature of inoculum plays a significant role in the production of MCC. So it's always better to, if a digester from a biogas reactor is used, it is very unlikely that one can get a significant quantity of the biochemicals produced. I think we gave this in details from these 2 papers. Now, another factor that could influence the production is pH, hydraulic retention time, organic loading rate, and temperature. Now, many experiments have shown that optimal pH for medium chain carboxylate production is 5.5, and the temperature is about 37 degrees Celsius. So to explain this, I will want to explain what we did with a given substrate sometime. To do that, we use a CSTRO. This CSTRO has a capacity of about 15 liters. However, we had a working volume of 12 liters. Now, remember that silages usually have low temperatures. As I said, silage usually have low temperature. Low pH, so of about less than 4. So whenever we add silages into the reactor, the pH tends to drop. But we usually require a pH of about 5.5. So what we did was to put a pH controller here, such that whenever the pH falls below 5.5, it will now suck in sodium hydroxide into the reactor just to keep the pH stable. Now, whenever we take out a digestate from the reactor, there's usually a pressure drop such that the reactor tends to suck up air into it. In order to avoid that, we connect some gas bags to it such that these gas bags tend to balance that pressure drop that the reactor usually experiences whenever it is open for the removal of digestate. Of course, we also connected this gas pipe to a gas meter where we measure the gas produced and even the quality of the gas in terms of the amount of methane or carbon dioxide contained in the biogas. To explain this again, we use rice hulls. Now, this is an ensiled rice hull. This is rice hull before ensiling. Now, rice hull does not contain much water-soluble carbohydrate. So in order to make up for that, we had to add molasses to it. So the CTRO was rice hull without the addition of molasses, while TRT is the rice hull that molasses was added in, while this one is the rice hull before ensiling. Of course, these are the properties of the ruminal fluid. So just as we said before, there was a significant drop. Of course, there is a drop in total solids and volatile solids. But one thing we observed was that there was butyric acid present in rice hull without molasses added. But the one that we added molasses had no butyric acid. So that means that this silage this TRT was better inside than this. But then it does not mean the CTRO was a bad silage, judging from the FFP point. I mean, the FP. The FP is called the flix point, and it is usually measured depending on the TS. So it means that a silage that has a higher TS has a better FP than one that has a lower TS. And of course, the one that has a lower pH has a better FP as well. So the higher the FP, the better the point. In fact, what we see here is that where a score is greater than 80, then it's very good, and so on. If it's 61 to 80, it's good. 41 to 60 is satisfactory. 21 to 40 is medium, and less than 20 is bad. So as we can see from the two silages, the FP was more than 80. However, the one that we added molasses was of a better quality than the one without molasses. So after this ensiling, we carried out the anaerobic fermentation of these silages. This was what we had. Now, interestingly, it shows something interesting. Now, the CROT, the one without molasses, produced a higher concentration of C6, C7, and C8 than the one we added molasses. And of course, we said before, as I mentioned before, that the one with molasses was of a better silage quality. Why? Because of the absence of butyric acid. Butyric acid is not needed in silages. So this one was better. However, we see here that this silage, the CTRO, had higher concentration of. Now, as I mentioned before, medium chain carboxylate is a series reaction where acetic acid is elongated to butyric acid, and then butyric acid is elongated to caproic acid. So in this silage, butyric acid was already in the system. So it was just simply elongated to caproic acid. That is number one. Number two, the microorganism that is responsible for the formation of butyric acid in silages is called the Clostridia. And these Clostridia are also responsible for chain elongation. Now, since this contains butyric acid, it means that Clostridia was already in the system and therefore started the production of medium chain carboxylate even early. From day one, we noticed the production of C6. But in the other silage, the better silage, now we didn't notice anything until the third day. That was when we noticed a concentration of caproic acid. So on the surface, one would think that this silage, although it contains butyric acid, was the better one. But that was until we now calculated the yield. We can see from the yield that TROT had a better yield than CTRO because of the loss, because the production of butyric acid led to a loss in VS. And so we needed more substrate for a given mass of VS in this case than in this case. So we had, even though this had a higher concentration, the yield was higher here than in the CTR. And so for the continuous fermentation, we use TROT for the continuous fermentation at different hydraulic retention times. We see that at higher hydraulic retention times, the concentration increased for for the 3 medium chain carboxylate. Now, in this case, we had a mixture of even-numbered and odd-numbered carboxylate. This was because the silage contained both acetic acid and propionic acid. So when one has silages that contains these two, we can have a mixture of odd and even-numbered carboxylate. Now, at higher hydraulic retention time, the substrate stayed longer in the reactor. Therefore, we are now susceptible to being converted more to the required product. This also happened when we use, even at very high hydraulic retention times, when we use pineapple waste, we got basically the same thing as well. For C6, this case was judged for C6, and we had higher concentration of C6, even at these high hydraulic retention times. So, yeah, we published this some time ago in this journal. So the question one would likely answer is how economically feasible is chain elongation? To answer this question, we carried out a techno-economic analysis using two economic indices, which were the net present value and the profitability index. Now, to do that also, we used two different scenarios. Scenario one was a situation where we produced only medium chain carboxylate. We extracted it using liquid extraction liquid extraction method. The other one was a situation where after the extraction of the medium chain carboxylate, we now use the vinasse, that is the liquid remaining after the extraction of medium chain carboxylate. It is usually populated by short chain fatty acids. So we now use it for biogas production. So these were the two case scenarios. And this was what we observed. Now for case A, which is the case scenario one, where we produce only medium chain carboxylates, our NPV value was negative, the PI value was less than 1. This economic indication shows that this is not viable. But when we use it for biogas production, when we use the vinasse for biogas production, the economic indices became positive. So one of the reasons why we had negative values was because of from the extraction process. As I said, we use the liquid extraction method to extract the medium chain carboxylate. And the solvent we used was oleal alcohol. And the extraction efficiency was only about 52%. That was quite low, because in another study where we used a different solvent, like the TBT, the tributyl phosphate, we had an extraction efficiency of more than 90%. In that case, we had these indices, the NP value was positive and the PI was 1. So for us, for an effective economic viability of chain elongation, the extraction method is key. Using a solvent or a method that will give a very high extraction efficiency is very important. And yes, we submitted this recently to a journal in Nigeria. It is yet to be published. So, what are the challenges and the future perspectives of this? Now, for the challenges, for an enhanced process, external supplementation of electron donors may be required. The point is that chain elongation requires acetic acid as electron acceptors, or if you like, the short chain medium carboxylate. And it also requires electron donors like ethanol and lactic acid. If these components are not enough, there may be need for an external supplementation. And this external supplementation, of course, will increase the overall cost of the process. Another one is the selective conditions are often required for an improved chain elongation process. So basically at times, like that pH of 5.5 that I mentioned earlier, apart from the fact that it helps to increase chain elongation, it also, at that pH, also tends to inhibit methanogens as well. So selecting an appropriate condition is very, very important. And sometimes there's just a thin line separating the condition that will favor chain elongation from that will favor methanogenesis. Now, chain elongation is highly sensitive to microbial community. So it is very necessary to use an enriched or specialized inoculum. Like one thing we have known is that biogas digested from biogas reaction or biogas reactor is a no-no. Now, the solvents for optimal extraction of medium chain are often quite expensive, and even the methods as well. Perhaps new methods should be developed in such a way that we can have cheaper solvents giving optimal extraction efficiency. As for the future perspectives, now it is like when we did the techno-economic analysis, if we can couple chain elongation with traditional anaerobic digestion to produce biogas, that may also be good in such a way that after the extraction of medium chain carboxylates, we can now use the vinasse that is remaining. Instead of discarding it, we can simply use it for biomethane production. I think that will also enhance the biorefinery process. Now, advanced separation techniques like nanofiltration could enhance extraction efficiency. Now, apart from that, recently I saw where some authors use adsorption to extract, the process of adsorption to extract medium chain carboxylate from a fermentation broth. And maybe this could be another method that one could take a look at, provided it will. And that method, that adsorption method, had an extraction efficiency of about 98%. I think that was high enough. And then engineering of specific microbiome for chain elongation could produce longer, because in all that we did, in all experiments that we have done, we have only had C6 and C8. We have never had C10. We have never had C9. And these ones are even more valuable than C6, C7, and C8. So if we could have engineered microbiome that could enhance longer chain elongation, that would also contribute to the economics of the process. Yeah. Thank you very much. And yeah, thank you for your time. Thank you so much.
Okay, wow. Thank you very much.
All right.
Coordinator, please go ahead. I was waiting for you.
I thought you were going to take over from there, but it's okay. Thank you very much, Dr. Diandoye. It's so nice listening to the lecture. It appears we don't have Professor Amenegawan here. So let me acknowledge the presence of our esteemed past president, Professor Sam Adefila. who is on this call. Thank you very much, Prof, for joining in. And we'd like to take questions and comments in the next few minutes. We've had an engaging session, and if you have questions, can you please use the raise hand icon so that we could take your question or comment, please. All right, Prof, let's have you, sir.
Thank you very much.
Sir.
You know, I try as much as possible to ensure that I attend this particular AG session because it's our own. And I particularly want to acknowledge that Dr. Udenwe is a real teacher, not because what he has done here, I don't know whether it's me alone, he taught us, not lecture. Because I was able to follow everything that he did right from the beginning. So thank you very, very much. The only problem is that how do we now ensure that he is able to advance the knowledge he has garnered together to so far to make for good applications for us in Nigeria. So as he was talking, really, because recently, one of the things that attracted me to the subject was recently somebody was telling me that he knows of somebody who is into, if you are into agriculture, if you just say produce yam or just produce cattle like that or so, you will not get so much until you further process, that's when you get more money. So he told me of somebody who was fattening cows, and he had about, say, 100 units of area for his farming. So he used about 90% of it to grow maize. And he was doing that throughout the year because he was using greenhouse, method, and just 10% of it to produce his cattle. So all he would do is just to produce to let the maize grow to a particular something, and then cut them down, and now process them so that you can have this. As Dr. Uday, so sorry if I butcher your name.
No, it's fine.
Talking, I was thinking of, because I follow the procedure which the people are following, and there are some relationships between what he is saying here and what they are doing there. So I wonder if you can discuss further with us your other applications beyond this pharmaceutical something which you mentioned, though that one is, highly valuable too. But can you discuss with us, extension of applications of this thing?
Okay, sir. Do I talk now or I wait for a next question?
As the chairman. Dr. Adewega, Emo, you can respond to him.
Yes, please. Dr. Dede should please respond. Or should we take all the questions? I think he should respond to that of yours, Prof.
Oh, okay. Okay, sir.
Yes.
Sir,
yes.
Prof, thank you very much for your question. My affiliation is
my question, first of all, for admonition. I admire your presentation.
Yeah. Thank you very much, Prof, for your very kind words.
Thank you.
Yes, sir. And my affiliation is with University of Port Harcourt, and I am closely working with some of my colleagues in some other universities as well. Now, as for the applications of the Ensiling and the medium chain carb carb carboxylates that we have, for the Ensiling, for example, we have used it for basically for now as a preservation method and as a pre-treatment method only, where we strictly ensile substrates that are only available seasonally. Now, for the applications of the extracted medium chain carboxylate, the truth is with my the truth is with my Nigerian collaborators, we have never done a situation where we have to extract the carboxylate for sale. But here, what we did the last time we did it, even at that 52% extraction efficiency that we had, we extracted the carboxylate and sold it. And that was how we were able to arrive at that, techno-economic analysis that we did. So in terms of the applications of the medium chain carboxylate here, when I was at the German Biomass Research Center, we used it as a precursor also for the production of sustainable aviation fuels. That was, I think, the only application that we had it back then after the extraction. So we have not really applied it beyond the production of medium or sustainable aviation fuel beyond that point. But it's possible we are taking a look at other applications as well. But for now, we have not gone beyond that.
Please try to extend it, particularly to agriculture.
Okay, sir. Thank you very much for your kind word and for that insight. Yes, sir, we will.
Thank you.
Thank you, sir.
Thank you very much, sir, for that stimulation. Do we have other questions? Other questions, please, or comments? Any hands up? Okay, Dr. Abatunde Esther, please.
Yes, sir. Thank you so much, my chairman. Thank you so much, our doctor, for such a brilliant presentation. I was just following up very well. And this is even my current research. And I'm very happy to be under your lecture this morning. So I just have some few questions, sir. I look at the inoculum you have used, like maybe around 3 different inoculum, like ruminant fluid and some other ones. But I want to ask, what is the best inoculum and what should be maybe the properties of such an inoculum that can actually function very well in the production of maybe biogas and then under anaerobic digestion. Also, how were you able to measure the amount of your butyric acid? Is it inside the system you're able to measure it, or what is it? I don't know. Maybe you have used a particular equipment to determine the amount of the butyric acid and some other acid that were formed. Also, I want to ask about the substrates to the inoculum ratio. What does it look like? Is it going to be like, we have to be like maybe the same ratio, or which one will give us the best or highest yield of biogas production for substrates and then the inoculum ratio? Thank you so much, sir.
Okay. Thank you very much, Ma, for your question. Number one, which inoculum is the best? Now, from my experience, the inoculum that gave us the highest concentration of medium chain carboxylate was a fermentation broth from a reactor that was already producing caproate. So what we did was that we collect that fermentation broth, we filter it, subject it to centrifugation, and then collect the solid particle, which we wash and then use as inoculum. That is what has given us the highest concentration of medium chain carboxylate. But in terms of the one that will give you the highest production of biogas, just as I mentioned, biogas production and medium chain carboxylate production are two opposing reactions. Now, any reaction that will favor biogas production will be inimical to the production of medium chain carboxylate. So normally, an inoculum that is populated by methanogens will obviously give you, will obviously be a better inoculum for biogas production. So, but in our own case, what I have observed is that if you have one that's already producing medium chain carboxylate, that's what you should use. Or in the alternative, leachate gave us a higher concentration of medium chain carboxylate than ruminal fluid. But the one for medium chain carboxylate production, the one that is a no-go area at all, is digested from a biogas reactor. So that is the one for that. Now, as for the inoculum to substrate ratio is usually determined, it's always a function of the nature of substrate and the properties of the substrate. So we usually, before we can use anyone, we usually determine it based on batch processes before we now up it up for use in a continuous process. To measure our carboxylic acids, we usually use HPLC here. So we just take a sample time for a different point in time, and then we filter and then we take the sample for organic acids determination using HPLC.
Thank you so much, sir.
Thank
My
you.
question are well answered. Thank you very much.
Thank you.
Over to you, the coordinator, sir.
Yeah, thank you. I don't know, I was muted. Thank you very much, Doctor. Any other question?
Good day, sir. Hello, good day. I was wondering, yeah, I get it down. No, I'm there.
Please ask your question. Okay, it appears it's an interference. Yes, I have a question. When you talked about the minimum number of days for ensiling to be 124, I need some further clarification on that. Does that mean that before you could have optimum benefit from your ensiling process, it has to stay 124, or that is the maximum number of days that it can keep your, it can preserve your feedstock? I need some understanding about that. And do we desire to reduce that day or to increase it?
Okay, sir. Thank you very much for your question. Of course, the desire is to have an aim achieved in the shortest possible time as possible. So the desire is one, for preservation, and two, for pretreatment. Now, I have seen a situation where pineapple peas, for example, were ensiled for 60 days, and there was no significant change in the structural carbohydrate component. So I have only seen a situation where ensiling was done for up to 4 months before we can have any significant change in the structural carbohydrate component. Of course, if we ensile for shorter days, the preservation is there. So the preservation component of ensiling is always there, irrespective of how short or long a time it is done. So the 120 days I was talking about was for the pretreatment effect, was the effect of the organic acid, the fermentation product, the organic acid produced on the structural carbohydrate component. These acids are weak acids. So less than 6, I have seen 6 months, nothing has happened. But I have not seen for 90 days, and but I have not seen the effect for 90 days. The point is, the longer the ensiling period, the better the pretreatment process. If we can have a good pretreatment effect on the silage on a short time, the better. But how we can do that is what I may not know at the moment.
Thank you very much indeed. And that is the point I was trying to point to. Second, in terms of commercialization and applicability, nobody will be willing to 120 days or months to get an effect. So that is, I think, a major area we can begin to look at to ensure that we can have the effect of ensiling within a very short period of time so that it can have commercial use. Thank you very much indeed for this insight. I appreciate it.
Thank you, sir. Thank you so much.
If we have exhausted our questions, now over to the coordinator to please continue with the proceeding. The chairman, technical committee, please.
Okay, thank you very much, my coordinator. We now invite Dr. Esther Babatunde to present. Dr. over to you.
Thank you so much, sir. All protocols duly observed. Let me start by appreciating our guest speaker of today, Dr. Jerome Ndiande, for a brilliant and insightful presentation titled Beyond Anaerobic Digestion, Ensiling for Microbial Chain Elongation. Thank you so much, sir, for finding out time out of your busy schedule to present this lecture to us today. And we have actually got a lot of insightful messages from your lecture. And so on behalf of the Nigerian Society of Chemical Engineers, Education and Research Sectorial Group, it is a pleasure to present this certificate to you. And then we ask that you take it from us, and possibly in the nearest future, we may call you again to come and present to us. So really appreciate you for this particular lecture. And thank you once again for making today's webinar a memorable and impactful experience for all of us. Thank you, sir.
Thank you very much, Matt. Thank you so much. I appreciate it. Thank you so much, Matt.
Okay, thank you, our guest lecturer. We really appreciate. Yeah, please, coordinator, over to you for closing remarks.
Thank you very much indeed, Dr. Esther and Dr. Ndiande. On behalf of the Nigerian Society of Chemical Engineer Education and Research Sectorial Group, I'd like to thank every one of us who took our time to join this call this morning. A particular note is our pioneer coordinator, Professor Ayo Adekuye, who just bowed out gloriously from the University of Port Harcourt recently. And on behalf of all of us, I'd like to say big congratulations again on your 70th birthday, sir. And we wish you a glorious retirement. Just like I penned down in my tribute, I know you will have more time to continue to impact, to continue to freely mentor, and to continue to do more for those of us coming behind, even as you drop the burden of University of Port Harcourt. And I wish you, on behalf of all of us, a wonderful retirement and sound health, and to enjoy all that you have labored for in the last 70 years. Thank you very much indeed. Again, I'd like to acknowledge every one of us and our past president, Samade Fila, who took time to be with us again today. Prof, we deeply appreciate your fatherly role and bringing tangibilities to the space every time. Thank you very much indeed. I could see Reynald Noss. I think Reynald Noss is an international friend who usually joins this. Raymond, we thank you very much for joining this call again today, and we hope to see you again next month. Every one of us that took time to be here, we appreciate you very deeply. Maybe I'm doing my assistant coordinator's work already. Please to come and thank us. But that said, next month we will gather again, God sparing our lives, to look at an interesting topic, and I hope you will join us again. Thank you very much indeed. God bless.
Sorry, can you give me just 1 or 2 minutes to say a word or two?
Go ahead, please, Prof.
Please, I just want to seize this opportunity to congratulate Professor Kuye. This is the closest we have been together since he entered our 70th floor. I hope, Professor Kuye, I hope you are not going to retire from the university totally. I hope you still continue to give back, as some of us are also doing. So, like I said to you one-on-one, honestly, I really appreciate you, and I know that from all that you have done, you have really done academics, proud. And I'm so happy for the rest of you two coming from behind. I'm happy, though we are very few here, just about 12 of us in total. I hope that others will join, so that as some of us bow out, others will come in. Because as Professor Kuye is entering the 7th floor, some of us are gradually bowing out into the next floor also, so that there will never be a vacuum at any given time. Thank you very much. Professor Kuye, congratulations.
Thank you. Thank you very much, sir. I really appreciate, and thank you very much, my coordinator, for keeping the flag flying. And thanks to everybody on the platform for your goodwill messages and various supports that I received. Of course, I'm not tired yet. I'm just stepping aside from university administration.
Yeah, thank you, sir. Thank you very much indeed, sir. Thank you, Prof. Adefila, sir, for that inspiring and fatherly intervention and wishes to our esteemed Professor Kuye. Yes. Dr. Bello, are you there?
Yes, sir. Even though I'm on transit.
Okay, I've already done your assignment for you, and I've thanked everybody on your behalf. So I think we can close.
Okay, thank you very much. Thank you. Thank you, sir.
Sorry, back to you, my chairman.
I will pray that as we return to our various endeavors, that God will continue to bless us. Next month, July, we are going to have a guest lecturer from UK too. So I wish that all of us will be expectant. You can see that the number of participants is actually dropping. It's not really good. We make make effort to bring these people, and when they come in, they might be disappointed with the number of people they see. Please, everybody, I want to encourage each and every one of us to help us to invite people. Imagine when you see the flyer, help us to share it with share it in all your platforms, invite your colleagues, invite chemical engineers to come and participate or listen to the guest lecturer. I believe everybody can always gain something in every meeting, just as we have had today. So thank you very much. Then again, if you have anything that you want to share, any good research outputs that you want to share that will benefit any of us or all of us, please feel free to reach out to us. Thank you very much, and God bless you. Bye-bye. As we bring the meeting.
Yeah. Bye. Thank you. Bye.
Thank you. Thank you, sir. Thank you.
Bye.
Bye, Dr. Esther.
Thank you so much, sir.
You think I will not get you? That it was you. All right. Catch you later. Bye.
Bye-bye, everyone.
Bye, Prof. Thank you, sir.
Bye-bye, Prof.